Today, we're going to discuss motions in polar coordinates. In particular, we're going to derive the velocity and accelerations in polar coordinates, the box equation right here. And we're going to use these formulas to solve a problem. First, let's review the basics of polar coordinates. To establish a polar coordinate system, we choose a point as the origin and a ray that passes through that point as the reference direction. We can then use two numbers to specify the location of an arbitrary point in the coordinate system. The distance from O to P is called r, and that's our first coordinate. The second coordinate is given by the angle theta. We can relate r theta to the usual Cartesian coordinate of P. By basic trig relations, we see x equals to r cos theta and y equals to r sin theta. This defines a polar coordinate system. Then let us look at the notion of coordinate lines and unit tangent vectors. In particular, we're going to compare these notions in polar coordinates versus them in the Cartesian coordinate. A coordinate line is a curve on the plane such that one of the coordinate is constant. The coordinate lines in the polar coordinates are given in the first picture. When r equals constant, we have circle center at the origin. And when theta equals constant, we have lines passing through the origin. On the picture to the right, we have coordinate lines for the Cartesian coordinates. When x equals constant, we just get vertical lines. And when y equals constant, we have horizontal lines. Now let's look at unit tangent vectors. This is how we construct them. For example, for this point right here, this particular circle is one coordinate line, and the horizontal line is another coordinate line. Then we're just going to draw unit vectors tangent to those lines. The unit tangent vectors also point towards directions in which one of the coordinates is increasing. For example, ER points towards the direction that R is increasing. So ER points outward. And E theta points towards the direction where theta is increasing, because theta increases in the counterclockwise direction, and that gives us the direction of E theta. Of course, we can construct ER and E theta at any given point. So for example, I've drawn two sets of ER and E theta at two different points in the polar coordinate. The same concept can be applied to Cartesian coordinate. And the situation is actually a lot simpler, as the unit tangent vectors are just the usual I and j vectors. If we compare these two pictures, we have the following key takeaway. The unit tangent vectors in polar coordinate system vary from point to point. In Cartesian coordinates, things are a lot simpler. I and j does not vary from point to point. And this is going to have major implication when it comes to discussing the velocity and acceleration in each of these coordinates. Let's consider the position vector. The vector starting from the origin and point towards an arbitrary point on the plane. We then consider the components of the position vector along the unit tangent vector directions. In Cartesian coordinate, we can write rho equals to x times I plus y times j. In the polar coordinates, we can write rho equals to r times e theta, because r is just the length of rho and er is a unit vector. Then velocity and acceleration. Those are just first and second order time derivatives of the position vector. The definitions are the same regardless of our choice of coordinate system. Let's use the product rule. In Cartesian coordinates, because ij does not change from point to point, therefore di dt and dj dt vanish. We're just left with this nice formula. However, in polar coordinate system, the situation is different. Er dot is clearly non-zero because we mentioned earlier, Er and E theta vary from point to point. Our new objective is to investigate how do unit tangent vectors change in the polar coordinate system. From the diagram, we notice at each point, Er and E theta can be expanded in terms of I and j unit vectors. Then we take time derivatives on both sides. You just need to differentiate the components. I and j are left unchanged. We notice theta dot can be factored, and what's inside the bracket happens just to be E theta. Therefore, we have shown Er dot equals E theta times theta dot. Similarly, we can take the time derivative of E theta. To summarize, Er dot equals E theta times theta dot. while E theta dot equals to negative ER times theta dot. Now we have everything we need. We can then quickly walk through the derivation of the velocity and acceleration. The velocity v equals to d over dt RER. By using the product rule, we have r dot ER plus r ER dot. We then just going to replace ER dot by theta dot times E theta. This tells us that the velocity has two components. The radial component, r dot, and the transverse component is r theta dot. To get the acceleration, we'll just differentiate v one more time. For these two terms, we apply the product rule separately. The ER dot can be replaced by theta dot E theta. And now it is just a matter of collecting terms, and we can get the components of the acceleration. So the radial component looks like r double dot minus r times theta dot squared. And the transverse component looks like r theta double dot plus 2r dot times theta dot. And this completes our derivation. Taking a closer look at the acceleration formula, we might notice something rather unusual. The radial component has an r double dot. This is quite understandable. That is just a contribution due to the second order derivative of r. What follows after, namely minus r theta dot squared, is what we call centripetal acceleration. Because in polar coordinates, r is always non-negative, centripetal acceleration always points towards the origin. In the transverse component, the first term is rather understandable. That's the contribution due to the second order derivative of theta. The term that comes after is perhaps a little bit surprising, called the Coriolis acceleration. We'll look at the effect of these acceleration components when we investigate fictitious forces, which has significant impact in real life. For example, centripetal acceleration is the reason that you don't fall off roller coasters. The Coriolis acceleration is the reason that hurricanes spin, and also this is one of the causes of bullet deflection in long-range gunnery. This will definitely be a topic of future video. All right, we've done enough theory crafting. Let's look at an example. Starting from the point r2k theta equals 0, a particle moves with constant speed v along the upper half of the curve called a cardioid without reaching the origin. We're asked to find the radial component of the acceleration, the magnitude of the acceleration, and theta dot. Express your answers as functions of time t. So first, let's explore the shape of the curve. Here I made a table listing the value of r for various values of theta. From the table, we can then plot the curve like so. Since the particle moves at constant speed, at any time t, the length of the arc traveled by the particle equals vt. It follows that the position vector is also fixed. So in principle, we should be able to solve for theta of t. After that's done, the motion is completely specified because we already know the relationship between r and theta. So here's our solution. So using the velocity formula we just derived, we have v squared equals to r dot squared plus r squared theta dot squared, with the left-hand side being constant as given. We can substitute r theta into the previous equation. This simplifies to k squared theta dot squared times 2 plus 2 cos theta. Then we're going to use the half angle formula. We arrived at 4k squared theta dot squared times cos half theta squared. We wish to take the square root on both sides, but we have to be careful about the sign. Let's look at the picture once again. Because the particle moves along the upper half of the curve, theta is greater than 0, less than pi. And because it starts from the point 2k0, theta must increase. So therefore, we have theta dot greater than 0, and also cosine of half theta greater than 0. Therefore, after taking square roots on both sides of this equation, we'll just get positive signs on both sides. So this is what we get. V equals to 2k theta dot times cosine of half theta. This is the differential equation for theta as a function of t. Then I perform separation of variables, and this gives us 2 times the sine of half theta equals 2 omega t plus c. And I use the notation omega because v over k has a dimension of angular speed. Once again, due to the range of theta, that is from 0 to pi, I can invert the sine function without worrying about multi-valuedness. We can then use the initial condition to determine c. If we look at the picture, when t equals 0, theta is equal to 0. As a result, theta t is just 2 times the inverse sine of omega t. At this point, the problem is pretty much solved. Since r can be written as a function of theta, r of t is also determined. Now we know the exact polar coordinate of the particle at any time. And then we'll just use the formula we derived earlier for the velocity and acceleration in polar coordinate to find the desired quantities. The rest is just an exercise in taking derivatives, a fairly mechanical process. So I won't walk through each step in detail. What is interesting is that the radial component of the acceleration is a constant. The transpose component is a bit more complex, but it looks like this. So in order to check my answer, I first express everything in terms of theta, and I get a theta equals to negative 12 k omega squared tangent of half theta. Finally, we can combine the radial and transverse components to get the magnitude of the acceleration, and that's the final answer. That's the end of today's video.